We've already looked at the electron configurations for potassium and for calcium, but let's do it again really quickly because it's going to affect how we think about the d orbitals. And so we find potassium, which is in the fourth period on the periodic table, and if we do noble gas notation to save some time, we work backwards, and the first noble gas we hit is argon. So we write argon in brackets. And we know argon has 18 electrons and potassium has 19 electrons. So potassium has one more electron than argon. And so we put that extra electron into a 4s orbital because for potassium, the 4s orbital is lower energy than the 3d orbitals here. So we have increasing energy, and that electron goes into a 4s orbital. So the complete electron configuration using noble gas notation for potassium is argon in brackets 4s1. For calcium, I should say, right, we have one more electron than potassium, and so that electron is going to go into the 4s orbital as well. And so we pair our spins, and we write the electron configuration for calcium as argon in brackets 4s2. For the calcium 2 plus ion, so if you think about forming an ion here, we're talking about the electron configuration for a neutral atom, meaning equal numbers of protons and electrons. And so with an atomic number of 20 protons and 20 electrons. If we lose 2 electrons, right, we have a net positive 2 charge, so we form the calcium 2 ion. The 2 electrons that we would lose to form the calcium 2 plus ion, right, are these, right? These 2 electrons right here in the 4s orbital. And so the electron configuration for calcium 2 plus would be the same as the electron configuration for the noble gas argon here. All right, so for potassium, once we accounted for argon, right, we had 1 electron to think about. For calcium, once we accounted for argon, we had 2 electrons to think about. And so if we go to the next element on the periodic table, that's scandium, right? That's 1 more electron than calcium, so we'd have 3 electrons to worry about once we put argon in here like that. And this is where things get weird. Right, so now we have to think about the d orbitals, and once again, things are very complicated once you hit scandium because the energies change. So when you hit scandium, even though these are very small energy differences, now the energy of the 4s orbital is actually higher than the energy of the 3d orbitals, and so we're talking about, once again, increasing energy, and so that's pretty weird. All right, so if you think about these 3 electrons, right, where are we going to put them? Well, your first guess, if you understand these energy differences, might be, okay, well, I'm going to follow Hund's rule. I'm going to put those electrons in the lowest energy level possible here, and I'm going to not pair my spins, and so I'm going to write my electron configuration like that for scandium. And so you might think it would be argon 3d3. But that's not what we observe for the electron configuration for scandium. So actually, 2 of these electrons actually move up to the higher energy orbital. So 2 of those electrons move up to the 4s orbital here like that. And so the electron configuration turns out to be 4s2 3d1. So it's actually 4s2 3d1, or if you prefer, 3d1 4s2, once again with argon in front of it, so either one of these is acceptable. And so this is weird. Like, why do those 2 electrons go to an orbital of higher energy? There's no simple explanation for this, right? So even though it might be higher in energy for those 2 electrons, it must not be higher energy overall for the entire scandium atom. And so there are many other factors to consider. So things like increasing nuclear charge, right? So that scandium has an extra proton compared to calcium. And then there are, once again, many more factors and far too much to get into in this video. And unfortunately, there is no easy explanation for this. But this is the observed electron configuration for scandium. So how do we know this is true? How do we know that the 4s orbital is actually higher energy than the 3d orbitals? We know this from ionization experiments. For example, if you form the scandium plus 1 ion, the electron configuration for the scandium plus 1 ion, so we're losing an electron from a neutral scandium atom, this turns out to be argon 4s1 3d1, or once again you could write argon 3d1 4s1. So where did we lose that electron to form our ion? We lost that electron from the 4s orbital, right? We had 4s2 here, and here we have 4s1. So we lost this electron. And that only makes sense if the 4s orbital is the highest in energy, because when you lose an electron for ionization, you lose the electron that's highest in energy. That's the one that's easiest to remove to form the ion. And so the 4s orbital is actually higher in energy than the 3d orbitals. You don't see this a lot in textbooks, and I think the main reason for that is because of the fact that if you're trying to think about just writing electron configurations, and so if your goal is to write, let's say you're taking a test, and your goal is to write the electron configuration for scandium. And so the easiest way to do that, let me go ahead and use red here. So the easiest way to do that, if you want to write the electron configuration for scandium, right, you look at the periodic table, and if you're doing noble gas notation, right, the noble gas that precedes it is, of course, argon right here. And so that takes care of the argon portion. And then looking at the periodic table, you would say, oh, this could be 4s1, 4s2, 3d1. So that gives you the correct electron configuration, argon 4s2, 3d1. But it's implying that the d orbitals, the 3d orbitals, fill after the 4s orbital and is therefore a higher energy. And that's not true, actually. And so it does help you to just assume that's the case if you're writing an electron configuration, but that's not what's happening in reality. And we need to think about the other elements here. So we just did scandium, right? So next, let's move on to titanium. Thinking about titanium, so the next element in the periodic table, if your question on a test was write the electron configuration for titanium, the easiest way to do it is just once again to think about argon. So put argon in brackets, and then think to yourself, this would be 4s1, this would be 4s2, this would be 3d1, and this would be 3d2. So you could write 4s2 and then 3d2, or once again you could switch 3d2 and 4s2. And so once again, this is implying the d orbitals fill after the 4s orbital, which isn't true, but it does get you the right answer. And so it's useful to think about it both ways. It's useful to think about the energy levels properly, but at the same time, if your goal is to get the answer the fastest way possible, looking at the periodic table and running through the electron configuration might be the best way to do it on a test. So let's look at some of these other elements here. So we've just talked about scandium and titanium. All right, so let's go down here and let's look at this little setup here. All right, so we just did scandium and titanium. All right, so scandium was argon 4s2 3d1. So we talked about 2 electrons in the 4s orbital, 1 electron in the 3d orbital, and then we just did titanium 4s2 3d2. Or once again, you could switch any of these. And when you're doing orbital notation, right, adding that second electron to a d orbital. Here's the electron that we added, so we didn't pair up our spins, so we're following Hund's rule here. Next element is vanadium, so we do the same thing. One more electron, we add that electron to a d orbital, but we add it to, we don't add it to one of the ones that we've already started to fill here, right? We add that electron to another d orbital. And so once again, following Hund's rule. So things get weird when you get to chromium. So let me use a different color here for chromium. So if you're just thinking about what might happen for chromium, one more electron to think about than vanadium, right? So you might think, oh, let's just add that one electron to a 3d orbital like that and be done with it. So if you think about it, you might guess 4s2 3d4. So let's go ahead and write that. So 4s2 3d4. So question mark. But that's not actually what we get. We get 4s1 3d5. So that electron, so this electron here, let me go ahead and use red. So you can think about this electron. We expected it to be there. We expected it to be 4s2 3d4. It's like that electron has moved over here to this empty orbital to give you this orbital notation. Right, so that's just an easy way of thinking about it. And in reality, that's not what's happening if you're building up the atom here because of the different energy levels. But just to make things easier when you're writing electron configurations, you can think about moving an electron from the 4s orbital over to the last empty d orbital here. So some people say that this half-filled d subshell, let me go ahead and circle it here, this half-filled d subshell is extra stable. And that might be true for the chromium atom, but it's not always true, so it's not really the best explanation. The real explanation is extremely complicated and actually just way too much to get into for a general chemistry course. So Next element is manganese, right? Let me go ahead and stick with blue here. So manganese, one more electron than chromium here. So chromium, we had 6 electrons here. Manganese, we need to worry about 7 electrons. And so this is kind of what we expect, right? Just going across the periodic table. Let me go ahead and do this for manganese. Let me use green here. So you might say, okay, that's 4s1, that's 4s2, and then 3d1, 3d2, 3d3, 3d4, 3d5. So you might say to yourself, 4s2, 3d5. And so this kind of proceeds how we would expect it to. All right, and the same thing with iron. So 4s2, 3d6. All right, so that takes care of iron. And once again, now you can start to pair up your spins, right? So we've seen that in earlier electron configurations. Next, cobalt, one more electron to worry about, right? So 4s2, 3d7 makes sense, and you can see here would be the electron that we added, and we paired up our spins again. Nickel, same trend, right? So we add one more electron, 3d8, so that makes sense. Here's the electron that we added. And once again, we get a weird one, right? So when we get to copper, all right, so copper, you might think, so let me use red for copper, so we know copper is red. So if we think about it, we're adding one more electron. So if we took the electron configuration here for nickel, we added one more electron. You might guess that would be the orbital notation for copper. But that's not what we see. We've taken this electron here, right, and moved it over to here like that. And this gives us a filled D subshell here. So once again, one explanation you'll see for that is that this is extremely stable for copper, and that might be true for copper, right? And that leaves us only one electron here in our 4s orbital. And so the electron configuration is 4s1, 3d10. But all these general chemistry explanations are just a little bit too simple for reality. But, you know, if you're just starting out, they're a pretty good way to think about it. And then finally, zinc. Zinc makes sense, right? We're adding one more electron. So we just took care of copper. For zinc, we have one more electron. And so you could think about this being 4s2 right here, and then we have 3d10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 4s2, 3d10, or 3d10, 4s2 with argon in front of it gives you the complete electron configuration. And you can see you've now filled your 4s orbital and your 3d orbitals like that. So once again, pretty complicated topic, and hopefully this just gives you an idea about what's going on.